Hi, welcome to this HP Aruba networking update. I'm Kamal Takodra, a technical marketing engineer in the HP Aruba networking switching business unit. And today in this update, I'm going to be talking to you about PTP G.8275.1 and SyncE. So let's get into it. And in today's agenda, I'll be covering an overview, use cases, configuration, best practices, troubleshooting, and some additional resources. So I said earlier, AOS-CX 10.15 release 0005 introduces a new PTP profile and SyncE. So existing profiles are shown here. So it's 1588. .1 AS, AES-R16, SEMT, and AES-67. So the new PTP profile is G.8275.1, which is a telecom used profile in telco networks typically. And also synchronous Ethernet, which is shortened to SyncE, which we will do throughout this presentation, which I've already done. And SyncE is an ITU standard which is based on frequency and gives us a highly accurate clock. So just to summarize, we're going to be talking about PTP and SyncE. And so as of 005, I've listed here all the types of profiles that are available in our CX products, but today we're concentrating really on this first green column, which is G8275.1, and SyncE, which is the last column, which isn't a PTP as such. It's just synchronous Ethernet. And I've also brought out here G8275.2 just for completeness. Now it's not supported in our 10.15.005, but expect that to be supported in a later release. So this table is quite useful just to see some of the settings that you can have. It's a good takeaway, so you can pause this and look at this at your own leisure. So in terms of overview and terminology, I've put a few things together because some people may not be familiar, because this is now in a telecoms environment. So I've listed down here some definitions really, and some of the important ones that we will cover in this actual presentation. So I'll point these out right now. So typically we talk about a TGM, which is now with the T typically being telecom. So we have a telecom grandmaster, we have a telecom boundary clock, we have a primary reference clock, and we have primary reference time clocks as well. Now we also talk about GPS, which is based on US-based global satellites. We also refer to GNSS, which is basically taking up all of the satellites, including their GPS system, to give us more accurate information. And then we have GNSS receivers, which are multi-L-band receivers, which enable us to provide more accurate signals because they have multiple L bands, which avoid ionospheric delays. Now we'll cover SyncE a bit later. So we have Ethernet synchronous messaging channel, which provides us the quality of the clock when we're talking about SyncE. Then we get SSM message, which is synchronous status message, which are carried on the ESMC channel, which provide the quality level of the message, which is important in SyncE. And then I've listed the different quality levels that we're looking out for, which is QLPRC, which is the primary reference clock, and then QLPRS, which is the quality level of the primary reference source. Same but different ones for typically an SDH type of environment, so Europe, and then North America for QLPRS. Then we have the holdover, which is a time that allows maintaining synchronization when the external clock has failed. So this could be, for instance, when there's some maintenance being done. And then we have this free run period as well. So when a clock is running effectively on its own steam, typically when you've lost synchronization, and you're maybe typically running on your oscillator, and typically with certain products they can run free run for a number of hours without any significant degradation to the timing information. Now, just continuing the terminology, some important things we need to be aware of is something that we refer to as TE, which is the time error tolerance limit, which is typically in nanoseconds. And then we refer to different classes of boundary clock, A, B, C, and D. We'll be looking at basically achieving class C boundary clock level in this presentation with what we're supporting today, which allows long chain clocks up to 20 clocks and provides a TE, as mentioned here, of 30 nanoseconds or less. And then we have some information really about some of the setups, typically in a RAN or radio access network, and some of the details here. And I'll leave you to pause the video, look at the slide deck if you have access to that, and you can read that at your own leisure. But we do mention some of the important things in a 5G network just in terms of the basics. So we have something called central units that require timing information, and then we have distribution units that also need timing information in telco networks, typically 5G, 4G, and then those are placed in possibly places called front haul, which is between cell sites and the far edge, mid haul, which is between far edge and the edge, and back haul, which is between the edge and the core, and we'll go into some of that later in this slide deck. But please pause the video and please browse over these two terminology slides, because they'll be very helpful in understanding the rest of this presentation. So let's briefly go over SyncE. So it's a clock signal which is over the physical Ethernet layer, and it's based on a ITU-T standard listed here, G8752. Now the actual Ethernet synchronization goes over this Ethernet synchronization messaging channel, ESMC, which is carried between switches across Ethernet connection. Now this is a slow protocol with no control packets, but the synchronization messages themselves carry what I mentioned earlier with the QL, the quality level of the message, and there's a whole load of quality level information and clock traceability that again defined in various standards, but the one that we're looking for is QL PRC and QL PRS. That's sort of a thumbs up in terms of what we're looking for across to synchronize the onboard oscillators. So now let's add G8752.1 to the picture. So 8275.1 is a PTP and it's telecom profile which provides time of day, phase and frequency. Now, as we earlier learnt, SyncE is frequency based on the physical layer, using Ethernet frames, and allows us to have a T of 39 seconds or less, and by definition that I said earlier, so that's brings it within the Class C conformance. So what telecoms providers actually do is they use the SyncE frequency to assist PTP to minimize errors and provide us with much more accurate and strict timing requirements that are required in a telco network. So when we combine the SyncE and PTP 8275.1, we simply have now a Class C conformance with a TE of 39 seconds or less, and then we can provide a telecom boundary clock. So this allows us to provide the TBC. Now let's look at a use case. What happens if the PTP source is lost? Basically, what happens is that the PTP clock itself maintains frequency stability. Because of SyncE has a frequency reference, the PTP clock locks itself to the frequency that is provided by SyncE. So instead of going into holdover, the PTP clock is now frequency locked, and this allows us to carry on having accurate and strict timing as required by 5G or 4G networks even. So there's some requirements for having this to start things off. So in terms of CX, we have to have a PTP clock that is at least locked for 100 seconds before a PTP source. So that will happen at initialization. And the SyncE clock must be locked to a source as well. So that has to be done earlier. So that's all running now. And finally, the SyncE source must be either option 1 QLPRC, which we mentioned earlier, which is the quality, or option 2 QLPRS. 8275.1 and SyncE are supported in our 8325P platform. So the typical use case is in radio access network deployments, or maybe you would know it as 5G. So let's quickly go over this. So we have a few components here, which are the RUs, which is the radio units, and then we have the distribution units and the central units. So we would have the 8325P, which we highlighted earlier, using .8275.1 with SyncE positioned in where these dotted lines, dotted squares are. So at the far edge between the front hall and the mid hall in a classical centralized RAN, or you would find that in virtual DUs or virtual CUs between the front hall and the mid hall, or even at the edge in a VCU. Here we're drilling down further and zooming in on the use case, where you can see we've now created a centralized RAN pod which has our 8325P switches using PTP and SyncE, and providing that information or synchronization to virtual DUs and virtual CUs in this CRAN pod. So let's go into the configuration. So we're going to use this topology here to discuss some of the configuration options, and we're going to start off with enabling SyncE. So the first thing you need to enable globally is enable SyncE, and I've done that on both these switches here. Then you need to set the priority for the SyncE on every receiving port. So here this port is receiving the Grandmaster, and we've put a priority of 10, and we've enabled ESMC on that port. We've done the same on these lag ports too, which are receiving from this upstream switch. So we've got a sync priority of 11 and 12, and we've enabled the ESMC channel on both those ports. Now going back to this switch is only transmitting SyncE, so we've only got transmit only ESMC enabled for this switch leading to this switch. Now for client ports, which is this 11221 and 112 on this switch, we've just got ESMC transmit only enabled here, and then 112 down to this client here. Now, word on the priority earlier. So when you do configure a ESMC or SyncE, you must configure the SyncE priority first, then enable ESMC on the interface. Unless, of course, if the interface is a transmit only interface, then it doesn't matter. So that's the SyncE part. Now we're going to cover 8275 on the same setup. So you have to enable the PTP profile. So we've done it on both switches here. One step, transport to Ethernet mode boundary end to end. And then we enable PTP on the various interfaces. As you can see, we've done that on the Grandmaster here. Then the client port here, and this is lag 21, so we've done it on the lag here as well. And you can just see similarity on switch B where lag 21 has PTP enabled. Now the next step is obviously on this client port here, it's only a source only port, so we're doing that on this port here, which is a client port. It's a source only port, so we defined it as such. A lag 21 is also a source only port. And then notice in the lag configuration, we've selected, as you would with PTP, a primary and a secondary out of the two ports in that link. So it will always be going down the primary, and it will have a primary partner, which is on switch B, which is here for lag 21 on that switch, and the partnering port 112 on each, which is a secondary wire, which won't be used unless there's a failure. So that's quite a simple configuration to remember, a lot of terminology to remember, but in fact deploying it is relatively simple. So let's talk about some best practices. I've mentioned some of this earlier. So the PTP clock must be locked for at least 100 seconds before we have some sort of PTP loss, and to be able to keep to the Class C performance. And of course the SyncE clock must be locked to a source as well. And then the SyncE source must have an option 1 quality level PRC or a quality level option 2 quality level PRS. Remember, split ports can't have multiple PTP clients on the same physical port if you have a Grandmaster. So if you have a Grandmaster and PTP client on the same port, that should be avoided. Now, when you're bundling lag links, you must select the same link port pair role, and I showed that in the earlier config. So transmit and receive on both sides to avoid the loop, and it enables us to conform to Class C. And then for lags or trunks, the native VLAN must be used to carry the PTP traffic in between switches. And if you have clients that are using trunks for any reason, then it has to, and you're sending PTP, it has to be down the native VLAN. And then obviously use spanning tree for blocked ports, and to have a loop-free environment too. So let's go on to some troubleshooting. So there's a lot of information here, so please use this as a reference. So when you're looking at SyncE and global status descriptions, it's all defined here. What is the field? What is the meaning? And the possible values on those. For instance, the interface can be enabled, disabled. So please pause this video, or if you have the deck, take a look at this, or refer back to this if you are troubleshooting SyncE, or look at the fundamentals guide. let's do some basic troubleshooting for SyncE. So you could do a show SyncE interface, and we can see on this specific interface, it's enabled. We're receiving ESMC packets. It's a qualified clock. We can see the quality level is the PRC, and it's obviously the neighbor one hop away, and it's active receiving. Now we do that on another interface. We can see it's enabled receiving qualified, but we don't have a quality level, and the reason is that because it's timed out. So these two receive interfaces. Now we can also do it on a specific interface, and we can see that the status, it's enabled, but it's just a transmit interface. Now we can check the status of SyncE on a switch. So if we run the show SyncE status, for example, here we can see that the quality level is not PRC. We're running on the internal clock, the oscillator, and we're in free run mode. Again, running that command again, we can see that we actually got a quality level PRC. It's coming from 111, and we're in a locked state, phase lock state. And here, running the same command, we can see again we're not in PRC. We run to internal, we're in a holdover mode. That holdover mode is approximately 5 minutes, and after this period we would typically go into a free run mode, unless of course we then resynced. So that's the basics of SyncE and some of the troubleshooting commands available. So for PTP troubleshooting, use existing debug and show commands, and I've listed the debug commands that we can use for PTP, which are existing, so there's been no change there. And then we have the existing PTP commands that you can use to have a look what's going on, reference PTP. So in terms of additional resources, please refer to the PTP user guides, which can be found in the fundamental guides for each product, and specifically for the 8325P, I've linked it here. So if you have a downloadable deck, you can click on that link, or just search the Aruba support portal for the fundamental guides for the product you're after. And then here's the links for the ITUT specifications I've referenced, and you can Google those links, or if you have the deck, just click on the link. So that concludes PTP 8275.1 and SyncE. I hope that is useful and informative for you, and thank you for watching.